Hey everybody, welcome back to this course. In this video, we're just going to go over assignment 6 for EE 151. Um, so here's the assignment. All right, today we're going to need some copper wire, right, our Arduino kit, copper wire, SMA connectors, and we'll talk about what that looks like, and then just MATLAB again with these two toolboxes. So for this first part, we're going to be creating a quarter wave ground plane antenna. And I'd like to give credit to Yen Nguyen, another fellow grad student who came up with this idea. And we're going to be speccing it out for the 2.4 gigahertz Wi-Fi band. We'll talk about what that means. So then we're also going to be looking at the spectra of different modulation schemes in MATLAB. And then we're going to be designing an optical character recognition classifier, also in MATLAB, using this MNIST database. And I've got those files posted on Canvas as well. It gives you the instructions on how to get that set up, but I've also provided an example on Canvas. And then we're going to create a system that does something interesting, very open-ended here with your Arduino kit, and you're going to interface with at least 3 components. That's 3 components, not including the Arduino and breadboard, as some people have asked, right? So 3 other components from your kit. And then lastly, we're going to start thinking about our final project. I would like you to look for present research or read through hobbyist blogs and develop an Arduino project with a group, and then write a report that follows this IEEE research style, and then keep it under 6 pages. And we're going to be presenting our findings the last week of class, or recording a video for everyone to watch. So with that, we can go ahead and talk about this first part. So in part 1, we're going to be designing this quarter wavelength antenna, right? So we have some lambda Q that's going to be in centimeters. So we want this, and then we have F, so some frequency in hertz, and we have the speed of light, and that's in meters per second, right? So hertz is actually just 1 divided by seconds, effectively. So we can get something in meters, right? So we have like some lambda in meters, just by taking some length, right? Lambda is like lowercase l here. So we can find some length by taking c divided by f, right? So m by s divided by 1 by s, you get rid of that 1 divided by s here. And then you want to multiply by 1/4, you get this quarter wavelength. And then we need to, since we're in meters, we need to convert this to centimeters. And that's how you just get the optimal quarter wavelength using the information that's provided up there. And then, so I provided some background reading, or like a link to some hobby page that talks about the background theory for quarter wavelength antennas, and you're welcome to read on about that. But we're just going to be constructing one and looking at the frequency spectrum. So I'm going to be providing some copper wire, and you're going to get these SMA terminals. Kind of look like this. It's got a small cylindrical base, and then it's got these 4 ground terminals, and then this center terminal here, so the center conductor, right? And then we just get our pieces of wire and we solder it directly on to these terminals here. And all these wires are going to be of the same length. And that will be that. And then what I will do is I have some SDR, and my SDR can actually receive and transmit, so RX and TX. So for this exercise, we're just going to connect this to the receiver side, and we're going to look at the spectrum on a computer. So that is for the first part here. And we can talk about part 2. So in part 2, we're going to be looking at the spectrum, and I think I've stuck with amplitude modulated signals. So before we do that, let's just take a step back and talk about what what an amplitude modulated signal looks like, right? So up here on the Canvas page, I posted the definitions, right? So we have this phi sub am of t is the product of the sum of AC plus the message m of t times this cosine. So let's write that out. So phi sub am of t is our AC plus our message m of t. So AC is the amplitude of this thing called we call the carrier, and the carrier has some frequency, so 2 pi fc plus phi. So this phi is just some arbitrary phase offset, and we're just going to be setting it to 0. So I'll just actually erase this. Okay, so our message signal, right? Imagine that we're like just a radio station, because that's kind of easy, right? So our message signal can look like some kind of audio waveform, right? And it's got some audio, got some frequency content, right? And you could imagine if all the radio stations tried to play. So first of all, the audio falls within 0 to 20 kilohertz, right? So it's our audible range. Our ears are these receivers of frequency from 0 to 20 kilohertz. So we have this audio waveform, and you can imagine if all the radio stations, right? So if we had just have like a radio station here, we're broadcasting at this audible range, there'd be a whole a whole mess of noise. So what instead we want to do is we want to take our message, right? So Cal Poly has some radio station over here at 91.3, and this is frequency in megahertz. So then the next one down is 91.1, next one up is 91.5. And what we want to do is we want to take our message signal and we want to shift its frequency up in space, up in the frequency domain, so that all the content is encapsulated right here. So 20 kilohertz, well, these radio stations have about 0.2 in this direction and 0.2 in that direction to the next one. So we've got about 0.2 in total here, so 0.1 and 0.1. So we got 0.1 megahertz bandwidth for a radio station, which is enough to hold this audio waveform that we have. And this extra cosine that we have up here, this helps us shift our frequency, right? So we carry our message up to this new frequency in frequency domain. And so we have these definitions of different amplitude modulation schemes, right? So we've got double sideband suppressed carrier, and then I'm saying just do any other modulation scheme. I think FM is going to be a little bit more tricky, but there are some resources that automatically do FM modulation in MATLAB, which is nice. And so it makes note of these modulation indices. So we can talk about that really quick. So modulation index, and that is going to be the ratio of the amplitude of our message divided by the amplitude of our carrier, right? So this is a sub m. It's kind of embedded within this m of t, right? So it's not always clear what that a sub m is, but it's some peak amplitude of our message. And you can begin to think of just what happens if this mu, right, becomes greater than 1. Well, then that means that this ratio is above 1, which means that our message is larger than our carrier, which is at the point where we start to see distortion. And in the frequency, or sorry, in the time domain, right? So we usually have this carrier frequency. First off, the carrier frequency is usually much greater than the message frequency. So that's one assumption that we have when we make this amplitude modulated signal. And ideally, we want our carrier amplitude to be greater than the message amplitude. And that's just so that when we carry it up, we don't observe this folding effect. So when we have, suppose mu is equal to 1, well then our carrier, we have some carrier that's oscillating really fast, right? So here's our C carrier. Sometimes that's C of t. And then suppose we just have a message, that's just the tone, right? So one frequency message signal, M of t. And then our amplitude modulated signal, then at every part of our message signal, right, we have this modulation, right? So it's going up and down really fast. And our message is then contained inside of this is called the envelope, right? So we ride these peaks of our message. And we usually don't fold over to this negative side, right? So then what happens is when the modulation index is greater than 1, the message becomes distorted. It hops over this time axis. Right, so this is kind of what happens when mu is greater than 1. And you get to observe that with the example script that I've provided, and we'll take a look at that as well. Okay, so next up we have this optical character recognition classifier. And again, these are all really big projects. You only have to really do one, I think I said here. Yeah, I forgot to mention that at the beginning. So complete one of the following activities. These are much bigger, and I wanted to give you guys time to get caught up today. So right here, we're talking about the optical character recognition classifier. And then over here on Canvas, I've posted the images, right? So here's a bunch of samples of 0 provided by the MNIST database. And then there are a bunch of samples of 1. And so each sample is contained within a 28 by 28 pixel grid, I guess. We have this MNIST 0, right? And it's just this big file, but within this file, we have some 28 by 28, right? And then this is our sample. We've got our sample there. We want to extract the sample and look at each sample individually. So we have our sample. and it's just some image, right? So we can say like I is equal to that or something. I think I called it sample actually in my example script. So I is equal to that, and then we run a region props. Or so first of all, actually we start by taking the whole image. So I'll call this big one um, that has all the images I, and then we apply some threshold, right? So I is equal to I less than some threshold, right? So to make this a binary image, then we apply some threshold to convert it to binary, and then we start to iterate over each of the sub images, the subsamples here. And then we use this region props function to gather statistics on a sample image. Right, and we populate these two feature vectors. And once you have the statistics captured, right, we have this thing called feature space. So feature space, and we have some feature x1 and some other feature x2. And in a perfect world, right, we could have our x's be our our 1 samples, and our o's be these 0 samples. And in a perfect world, we could just perfectly separate our two samples, right, with this straight line, and have like a perfect classifier. But as you'll begin to notice, these are really big data sets, and the problem grows arbitrarily large as you include more and more samples of our targets. So that's for part 3. I think so I've got an example script that pretty much does a good portion of the steps, but what I want you to do is try it out on your own and see if you can do it before looking at this script that I've provided here. And so I'm not going to talk about part 4. That should be pretty straightforward. For part 5, I'm just going to quickly go over how to access some useful databases. And then also, while I'm at it, we'll walk over and look at these examples that I've provided. So right now we're at my desktop. Here's the example amplitude modulation that I've got going on. Right, so it plots the message, it plots the carrier, and it plots the amplitude modulated signal, and it plots this envelope, right? And then somewhere in the script here, right here is where you just change the amplitude modulation index, right? So you would change this to 0.5 and 1.5 and 1.0 and look at all the different values there. And then here's the optical character recognition classifier that I started up for you guys. Right? And I would advise you to try to work through it yourself first before looking at this. But it's a really interesting project, and it kind of shows you the power of MATLAB, I guess, right? So here's these original images, and if we zoom in, we can look at the individual samples. And I've gathered some statistics from it using this region props. Right, so I iterate over each sample. I grab the sample itself. So it's BW's black and white sample. Don't worry about this. We don't need that checksum anymore. But basically, with the samples that I have, it looks like a good decision boundary, right, would be around 34.5 or something. Just a straight line here. But again, that's not going to be a perfect classifier. which is okay. Right, so if we go to Cal Poly, your student portal here, or not your student portal, sorry, just the Cal Poly My Portal. And if you go to library, and if you go to databases, and you look for IEEE, well, I guess you just look for electrical engineering, and you can find this IEEE/IET. I think this is it. Yeah, so we get pulled to this IEEE Xplore page, and you can look for really anything that you want to learn about here. So let's just say I want to do a project on form intelligence or something. So I just look that up, and out pops a billion, no, not a billion, 11,000 papers on swarm intelligence. And this is a really excellent resource. I mean, these papers alone, if you were to just purchase them, each one costs about probably $30, give or take. And you can just click on it, click on the PDF, and read the paper. Right. So down here it'll usually say the price. Yes, it's a $31 paper right here that we're just accessing for free. So that's pretty awesome. So that's a good resource to get started with trying to figure out what you want to do for a final project, I think. And with that, I think that's all I wanted to talk about. So I will see you guys in the next video. Thanks for tuning in.